So hi guys, this is another developer meeting of Sky 360. I'm going now to demo the implementation of a timing hat, especially with the Waveshare NEO-M8T Timing HAT. So guys, you see my screen?
Yes.
Okay. So why is it, first of all, why is it important to have a PPS disciplined clock setup? We need time on a global scale. So every station shall have the same timestamps, if you call it the same time. So there needs to be a sync. And the only sync we have on a global base is via the GPS, GNSS time signals. The signals come in two ways. One is an NMEA signal, and one that is supported by atomic clocks in the GPS network. With a GPS dongle, you get an NMEA protocol of time just above the second. So you get the date, the time, and you get it down to a second, but not beyond the second. If you want to have real time, we need to use this PPS pulse signal, which gives us down to the very close two-digit nanosecond accuracy. So I went for the Waveshare NEO-M8T Timing HAT because it is very easy to install. So there's no need for soldering anything. All other products on the market do use a PPS output that needs to be soldered to a GPIO pin or jumpered to a GPIO pin if the board provides already a pin. Most boards don't. They just have a pin, not a pin, a layout on the PCB where you can solder something on it. So this Waveshare is a hat, a real hat, a GPIO hat, which fits exactly on the Orange Pi. I give you an image that you see what I'm talking about. So that's the chip. That's the board with the chip. Carlos, can you see? Yeah. Okay. So this is the board from Waveshare. This is the u-blox chip. It's the generation 8 chip, the M8T. T means timing. So they have a PPS output. They have a PPS LED on 0.4. They are the LEDs. And they route out on pin 12, which is on the lower pin side. It's 2, 4, 6, 8, 10, 12, P1. So it's routed here, this little route here, it's routed to P1. P1 is GPIO 12, which is GPIO 97 Linux-wise. And in order to make the kernel read the output, the edges on this pin, I needed to implement an overlay, a kernel overlay, which took me 4 weeks to solve that. Okay, so back to the page. This is the how to install. It's the GPS timing HAT installation MD file on our repo. And it starts here with this one. That's the first entry. So the signal of an NMEA is with an accuracy, it comes with an accuracy of about 10 to 50 milliseconds, but the output is just on the second. You don't get anything beyond the second, below the second. Only the PPS pulse with the accuracy for this head, for this chip, is about 5 to 10 nanoseconds, which I tested and is really exactly that range. And we have to feed both into, so NMEA goes into the system via the USB port, and the USB port is here, number 7. So all the data is transported via this port. Only the PPS signal is pinned out here on P1. So whenever you talk with this chip, you talk via USB, actually an implemented serial port. So another very important point is that a timing hat shall incorporate a battery, a backup battery, a rechargeable backup battery. The picture is here. So when you look at this board, this is flipped horizontally. So this battery plug here is underneath this area. And because it is of a height of about 3 to 4 millimeters, it's in the way of the cooling grid of the Orange Pi 5. So what I needed to do is to put the hat on the GPIO ports, so on the Orange Pi, so that it matches the pins 1 to 40, exactly with the 1 to 40 of the Orange Pi. But I couldn't pull that down as far as it should, because this part, the battery, is in the way. What I did is I marked the area on the cooling grid of the Orange Pi, and I cut it out so that there's a space in the cooling grid so that this plastic thing fits into. And now the head sits flush on the Orange Pi. Underneath it has the cooling grid, and this is, let's say, without inflicting geometry in this hole in the cooling grid. Do you guys understand what I'm babbling
Later
here?
on, when we have more than one board, then they all need to connect to this pin,
No.
right?
Yes. So the idea is we have a two-split thing. We of course have a disciplined clock on the board, on the local one. So we don't have to ecal this because it's on the board. You just call it time NS and you get the nanosecond accuracy. If we want to transport
Oh,
this,
what I meant is that this pin needs to be connected
yeah,
to all the boards, right?
yeah,
So this
yeah,
board can actually be outside. We can do a box, a printed box, and keep it outside so that we connect all the other oranges to it.
for example, yeah, that could be. We could do a little breakout board, simple one,
Mhm.
with just the pin headers that are connected, and we plug every board onto this pin. The next thing that then
Yeah.
needs to be done for every board is, of course, to implement the overlay. Yeah.
Yes.
So,
what about the problem of too long lines? If the wires are too long, then we get inaccuracy because of the time delay that comes with it.
I did
It will
calculations.
still be more efficient.
Yeah, sorry,
I
Gabriel.
was just going to say that it's still more efficient than
Yeah,
actually like broadcasting the time through Wi-Fi or even
network.
Ethernet, wouldn't it?
Yeah, true.
So,
Christian, we
so
have a delay of
the
about,
length of the wires is not very important to this short distance.
that's correct.
It
So,
might be important, but I think it's still better than broadcasting through Wi-Fi. I'll
may I,
say.
guys,
Okay.
can you hear me? May I give you an idea about the delay that
Yes.
per meter? It's about 5
Hmm.
nanoseconds per meter. We have an accuracy of 5 to 10 nanoseconds. So every meter
Okay.
doubles this inaccuracy. But if you go with boards that are close to each other by 20 centimeters, it's just nothing more than 1 nanosecond delay.
Yeah. So we're good.
Yeah, absolutely. Absolutely. Okay, going back to the battery pack. Why is the battery so important? The battery keeps the flash RAM alive, let's say. There are two RAMs. Both are flashy RAMs, but the one is dying on reboot. The other one is kept by the battery. And the order of priority is interestingly the other way around. So there is a flash memory, there's a BBR memory, and there's RAM. On boot up, the flush data is loaded into the BBR. And this is loaded into RAM. So what we need to do in order to survive reboot, we need to write the configuration into the flush. I also write it into the BBR, so to have it both, because when there's a boot up, then the flush content is copied into the BBR backup RAM. Took me days to find this out, but it works. I did reboots all the time. I think it's now at 23 boot or so, and it survives reboots. The almanac is kept, which is when I power it up, you have within a couple of seconds, let's say 2 to 5 seconds, you have a time, a 3D fix, and you have a PPS clocked distributed clock. So this flash stuff that is kept alive with the battery also keeps the receiver configuration, also the oscillator configuration. Oscillator configuration meaning how long the length of the pulse signal and the frequency, how often it comes. And of course the GPS last known position. Without the battery, without the battery, it's a cold start basically, configuration is lost, and satellite acquisition takes 30 seconds. Okay, so this is about point 2 where I'm talking about the modification of the cooling blade so that this part, the bottom part with this cell, battery cell fits nicely onto the cooling grid of the Orange Pi 5. So it's a 60-meter hole and it's easy to find. It's not really fiddling. You don't have to solder, but you have to cut a hole. And I think cutting a hole is much easier than soldering. And by the way, all other equipment that is not GPIO pinned has also most of them, actually all of them, the battery on the bottom side. So wherever you put it, consider that there is something on the bottom. Okay, mounting is actually totally easy. The GPIO pins fit perfectly. The board sits flush on the cooling grid and nothing is outside the board. So it's not hanging outside as, for example, there are examples where it's hanging outside. Oh no. I want to show you an image, it's never there. Here, on the Jetson, for example, it's the other way around. The numbering is different, so the board hangs on the right side outside the board. And in our case, it sits totally flush on the board. Okay. When you add the Waveshare board onto the GPIO pin, and you can really press it on until it is flush on the cooling grid, you also have to add again the fan pins, which is pin 4 and pin 6, so that the pan is also rolling. So next step is to configure the GNSS receiver. Created a Python script. It's under Tools, Time Tools. It's called Setting Timing HAT PPS. What it does, it creates a serial to the u-blox chip. It polls the current configuration, applies the new configuration, and I'll tell you shortly what the new configuration actually is, and saves the configuration to the flash RAM. Flash RAM, not flash RAM, flash RAM. And when it is done correctly and you get all light screen, let's say, then you can also test the PPS edges. So it has a test routine inside, so you can see when the edges are coming, falling or raising edges. So I configured There's a lot of other configurations that need to be set in order to have the PPS on the GPIO. So although the electronics is having a route between the output of the chip and the GPIO pin, is not necessarily meaning that you really get a time pulse there. You have to configure the chip for doing so. Okay, so there's a lot of configurations that I'm not telling you. If you want to know them, they are in the script. You can look them up in the PyScript. But most important is the pulse per se, so the pulse length and the frequency. I set the frequency to 1 Hertz. So once per second, we get a 50 millisecond pulse. That's rather reasonable for timing machines. I read papers together with ChatGPT. We sourced other papers and looking for what is the best configuration. And short pulse lengths, there's a sweet spot. The pulse length shouldn't be too small because we have edges that are, it's all analog. So there's a rising edge and a falling edge. And it doesn't make sense if they are too long. And the frequency shouldn't be too high because when you update the PPS signal, you get already per second a nanosecond accurate signal. So this is let's say a good setup. Next thing that you need is the GPSD daemon, of course. If it's not installed, we need to install it, including some clients. One of the clients is CGPS, which gives you an idea whether this already got a signal from satellites and by that a 3D fix. Because the PPS output is only coming with a 3D fix. There is the option in u-blox actually to have a PPS output when there is no 3D fix, but you cannot set it. It has two in the manual. It has the options in yes or no, enable, disabled, but you can't disable it. It's always the 3D fix has to be there. So I think they prepared it in the API, but they didn't really wire it. Yeah, importantly, GPS needs to be started with the -n configuration in order to create a shared memory, because the data exchange on the between chrony and the NMEA output is via shared memory. That's the only way where both chrony and GPSD are able to communicate. There is another option if we go with NTP instead of chrony. That could be using sockets as well, but it needs tons of other configurations. So GPSD and chrony are the most simple things to do, and they deliver. So I went for this route. Okay, so this is CGPS telling you have a fix, and when you have, then you also see the so-called PPS LED on the board blinking, which is, damn, where is this picture again when you need it? Yeah, anyways, there are 4 LEDs, and this is the power LED, the very left one. This is the receiving LED, this is the transmission LED, and the transmission LED is blinking once per second, and also the PPS LED is blinking once per second if PPS is configured correctly. So next step is to make the kernel read this stuff from the GPIO pin. In order to do so, I needed to create an overlay. Took me ages to find the right configuration for an Ubuntu on a rock chip, but finally I got it. The pin 12, GPIO pin 12 is on an Orange Pi 5, actually chip 3 and line 1. It has 5 chips dealing with the GPIO pins, and it's not that easy to find the pin numbering matching. So when you know it's physically pin 12, you do not know immediately which chip it is. So I had to test all lines in order to find out. So that's the file that you create, a DTS file, and you compile it, you get a DTBO file, and you also have to enable it in the so-called configuration, which is ambient environment text for Ubuntu on an Orange Pi 5, where it says just overlay is this configuration. Then you need to reboot, and what you now get automatically when the kernel is using this overlay correctly, then the kernel is creating a device PPS 0. So the GPIO interrupts are then triggered via this virtual device, PPS 0. I'm going to show you what PPS test is actually doing. It finds edges. So what you see here are the edges. I can configure it as falling or rising edges. And what you see is once per second, a rising edge. Means when the signal, the interrupt comes from a low to a high. You could configure it the other way around as a falling edge, but yeah, I've chosen the rising edge. So that one. Yeah, so the kernel now is receiving PPS pulses. And now it's easy for chrony to pick that up. So you have a chrony configuration. And you have the PPS clock on device PPS 0, which I showed you at the moment before. And you have the shared memory where the GPSD is writing NMEA protocol into. The others are configurations which make chrony just reliable and speedy for PPS signals. Restarting chrony gives you immediately a output like. Are you guys still with me?
Yeah.
Yes. Okay. Thank you. Okay. So what you see here is the output of chronic sources, and it defines the PPS with a star, and star means in use, and the minus means that it is available and in use, which is funny. I don't know why it is like this. That why don't you use 2 stars? But they make a differentiation between GPS because there are more options in GPS. There's a plus, there's a minus, there's a star, and 2 other things, I think. For PPS, it's only a star or a question mark. For GPS, there are more options. So minus says it's there and it is used. And what you see here is on the right side, you see an average of 11. Wait a second, where's the average? Plus minus. Yeah, it's a microsecond. Sorry, this is nanosecond. So this is 9 microseconds. The average is 11 microseconds for the NMEA, so for the down to the second signal. And then other way around. This is the 11 microsecond accuracy for PPS at that particular point in time when I started it. So it varies all the time. And it does it hundreds of times per second. So it gets one signal once per second, and then it adapts the PPS. So it goes down. The accuracy is getting smaller and smaller. Maybe showing is much better than talking. Yeah, you see how these values vary over time. Okay. So you see we are in the microseconds on the PPS and we are on the milliseconds on the GPS. Nanoseconds, actually. but that's another output I need to show you. Okay, that's the verification I showed you. Then there's a point, the almost last point is a full validation checklist. Check that you see this, and for the final result, you should end up with a disciplined clock with about 5 microsecond accuracy and on the PPS pulse, and about 50 milliseconds accuracy on the normal timestamp, which is much lower than 1 second because it comes with a second accuracy. So the real accuracy is in the PPS pulse. And Linux disciplines the clock, the system clock, down to the microsecond. That's basically it. I can now say, Christian, Carlos, that you can go for the Waveshare. You just plug it on and you don't need any soldering nor such extra work done. Just the cutout of the cooling grid. That's the only it needs to be done. So the battery is there. Questions?
Have you tried using a GPIO pin multiplier, like an extender that has more than one output?
So to use more than pin 12, you mean? Pin 13, pin 14 or so?
You can get a pin multiplier where you have got, I think, at least double the output. So you've got one GPIO pin set to the right, and the other one is above. So you can use two heads.
You want to use two
you
heads?
use a cable for the other output.
I think I do not understand what you really mean. You want to go with two heads?
Yeah, we talked about it, I think, 3 years ago.
Okay.
That it's possible to do memory sharing over the GPIO pins with around 10 microsecond in delay.
Mm-hmm.
I'm going to post a link to the...
I think we should make our life much easier. We have a GPS on one board. We can propagate the NMEA via ROS2 because this is only from 1 second accuracy anyways. And do the PPS signaling over GPIO wires that we just jump from one board to the other. That would be my proposal. Carlos, what do you think? Can you hear Carlos?
Yes, sorry, I was muted.
Okay.
Yeah, so can you hear me now?
Yes.
Yeah.
Okay, yeah. Yeah, so what you're proposing is to share then through Ethernet or something?
Yeah, so from board to board, we use ROS2 network. And we propagate the timestamp, the NMEA timestamp, which is only accurate down to a second, to 50 milliseconds or so, something like this. Where is it?
What I saw that was more efficient would be to actually connect each board to the same pin physically.
Yeah. But don't forget, we have two different types of information. We need both all the time. The NMEA plus the PPS. The PPS comes via the GPIO, and then NMEA comes via the USB into the board. And now we have from this board to propagate to other boards via ROS2, because we have low latency, and I think that should be around 50 milliseconds anyways. We have the NMEA timestamp there, and then collect the PPS signal via jumpered wires from GPIO to GPIO. And then implement an overlay on that board, and it's there.
I put a link to Amazon for the GPIO extender into our chat. So That's what I was talking about.
What is this doing? Can you explain?
It just multiplies the GPIO pins. So you can connect more than just one to it. It has got,
Okay.
you plug it
Physical.
in, and you've got the ones standing out above and one to the right or to the left.
Yeah. I'm
like
not
you
sure whether
prefer.
we need this because when I put this board, the Waveshare board, onto the GPIO pin, you get, with the Waveshare board, you get an extra, how do you call it, a row of pins that you hook on the pins on the Orange Pi, and then you put your board on top of it. Do you know what I mean?
Okay.
So
Yeah,
there's a picture
some
where you can
kind
see
of
it.
extender, but only for
No.
longer pins.
Look at this.
Yes.
So normally this gray stuff is not on the board. This gray. That's this barrel of GPIO pins that you can just buy anywhere and put on a board. And what it does, it just elevates the pins from the board up to a centimeter or so.
Yeah.
And then you put your board on top of it. And the only things that are covered here is with the fan. They sit on pin 2 and 4. And the rest is open. So everything can be jumpered here. Okay.
Yeah, I was thinking of if cutting something out means you have to alter the cooling heads or so, it might be interesting to have some kind of spacer that multiplies the GPIOs, GPIO pins.
Absolutely. You can
at the same time.
Yeah, you can use 2 of them over each other, for example, or one that you showed us that goes to the side if you want to. Yes.
Yeah.
Then mounting the board like this, you don't need to connect through USB, or you still need to connect USB to it.
The reason for this board to exist is that the data and power is routed over the GPIO pins. So the whole board is powered by the GPIO. And because GPIO is there, it already delivers the PPS here. But all other stuff, NMEA configuration, goes over the USB.
Yeah, so that's the point. Even inside the box that we have at the moment, you still need to have a cable, a USB cable going in.
Yeah.
Or okay.
Yeah. There needs to be a cable from here to a short one. And the fun thing is, it's not to power the board. So this USB is only for the serial.
Right.
Yeah.
Yeah, we need to think of a design because how to share with the other boards as well.
When I think about it, the idea of Christian with the side stepper, the GPIO side stepper, is actually not that bad, because we could in this case we could mount the head on the side and let it set up vertically.
Yeah, and there are GPIO pin cables available. I think a pack of 5 around €15 that can be used to provide the GPIO pins to other boards.
Like the all
not directly mounted on top of each other.
I would not go with. Sorry, Nicola, go ahead.
Yeah, go on, please.
Go ahead.
Like all the parallel ATA cables, which are like ribbon cables, which you plug into entire GPIO header and route it wherever you need it. And plus you have multiple headers on it. Is this what you mean? Just to mechanically separate the boards, so you don't need to cut heat sinks.
Yes.
Yeah, but also we should think about multiplexing our PPS line. For example, later on, maybe we will have multiple cameras which have external exposure trigger, which can be hooked to PPS.
Yeah, of course. The interrupt is there, yeah. So your idea, like a parallel cable to connect boards, I'm not sure whether this is really a good idea, because every board and kernel have a different layout of the GPIO pins and how they use it. So it took me a while to find out that the Orange Pi 5 has 5 chips working on the GPIO pins. So when you use a standard cable, 1-to-1, you probably only can connect Orange Pi 5 boards. And then there's my question, what about the hotlines? So
Yeah, but if you have in multiplying extender, then you can use different versions of the cable, or just
we just need one pin.
use
I mean,
the cables separately to connect something. But you have the possibility of using that one Orange Pi 5 to be the heartbeat inducer to everything else.
Yeah, which it is already with a GPIO pin 12. So you just put a jumper wire on it and to another board, and there you go.
But maybe if we need some other pins for something else, then we can have that too.
Yeah, of course.
That's why I had the idea of using a multiplier for the pins.
But not all pins are available. Some pins are already used by processors.
Yeah.
So it's not just that you have
Just need to multiply PPS.
Excuse me, once again.
If we are going to multiply anything, we are going to multiply PPS line, right?
Yeah. Yeah. So what we can do is just to have a line. I'm missing the English word for this. Where you have let's say where you have just 10 pins, for example, but all pins are wired together. So if you have 5 boards,
multiplexer, one to many.
A simple multiplexer where you just have 5 cables.
But hard-coded multiplexer.
Hardcore, yeah, of course.
Where it's always broadcasting to all pins.
Exactly, and not to all pins. You go out from your Waveshare. You go out on pin 12 with a wire jumper, with a jumper wire, not wire jumper wire. And let's say of 10 centimeters, 20 centimeters length. And you go into pin 12 on the other board. So now the other board gets the same interrupt because there's no other process creating an interrupt there. And you need an overlay for the kernel, and the kernel can read the PPS there, created by another board.
So if this other board is, let's say, Raspberry Pi or Jetson, you just need to install chrony and as an NTP server or what it is, and to say, okay, GPIO 12 will be PPS sync.
Yes, exactly. In theory, it's exactly what you said. In practical, it depends what board you use, whether you can go with the standard. With the Raspberry Pis, it's kind of a GPIO 12 is actually GPIO 18 or so. A little bit odd. I did go this route. And if you use Ubuntu, then you certainly go with an overlay, a kernel overlay. It's the fastest thing you can do. Anything beyond interrupt reading is time consuming. So yes, basically yes, you can jump onto different boards. You just have to configure each board for itself. If the board is not an Orange Pi 5 or an Orange Pi 6.
So you set on which pin you are actually receiving, because there are logical pins and physical pins on each single board computer.
Yeah, you just have to, if you, for example, a stupid example, you take an old Raspberry Pi 3, which I'm not aware of GPIO pins at all. I have no idea how it is.
I have one, I can confirm it.
They do have, I know that they do have, but do you know how they are used? So it means,
Oh, no. I usually need to consult the mapping layout. There is
yeah,
an image depicting your physical layout and then how it's connected to the CPU itself, how it's
yeah,
mapped internally.
yeah. And look especially whether there's just one chip or several chips consuming GPIOs and what processes are running there. But if you find you can use any pin that is free. Just put the PPS, the wire the jumper wire there, and configure your kernel. If you go with with Ubuntu, the kernel is easy. I mean, you can adjust this. Where is it? Here it is. The only thing that you need to find out is which chip and which line it is actually. So I can give you an idea. How is this working? Probe. What's this called? PPS Mon. Is this called this tool? I didn't write it here in the. Yeah, I forgot this tool. Damn. Blödsinn. The I/O monitor. That's the word. Is it this one? GPIO monitor. So, go for chip 3, and the line. Okay. And if I take another one, so I have to find one that is in use. I have just to guess now. 23. Okay. I'm not prepared for this question. Sorry, guys. But that's the way it is. So with GPIO monitor, you just look, is there a process running on this kernel that is using this particular pin? Until you test all and you find out this is the one that is remaining. These are the ones that are remaining. And then you configure your overlay like this, especially when you know where it is. Yeah, especially when you know that this Waveshare HAT is indeed routing out to GPIO 12, which is physically on the board itself. That's a line. It's a hardware line. But the fun thing is the hardware line.
But that's because you're placing the chip over it, right? Because if you have the chip outside, then you can connect to any pin.
Yeah, absolutely. Absolutely. Any free pin. Yes, that's right. Yeah, that's true.
And so that's why I still think it would be more efficient to have it outside in the box.
Yeah.
Then we can define the box, and then we have cables coming out of it and just connect to the port that we want on each one of the oranges. And if we have Raspberry Pi or something else, it's the same process, and we can just put the correct
Maybe on a
peripheral
different
in
pin,
there.
yeah, on an appropriate pin.
Yeah.
If we go just with Orange Pi 5s, we can only plug on 12, 12, 12, GPIO pin 12, GPIO pin 12, and we just use the very same configuration.
No, it's just if the board is outside, then you can just use any pin, and so then you can define pin 1, for example, and then it's the same for all the boards. I just need to connect to the pin 1 for each specific board. But from the code perspective, you don't need to change anything. So anyone fetching the code, they can use it directly.
Yeah. So using the code, so the configuration code is more or less independent because it reads from device 8me0, which is a serial in this case.
No, what I mean is that you're placing this board on top of the orange.
Yeah.
So the pin out needs to match, basically.
Yeah.
And if you get the board and put it on a Raspberry Pi,
Yeah.
then you need to find out what is the pin
Yeah.
that is going to match the output from the board.
Yeah.
And so then you need to change the code so that you are looking for the same pin. What I'm saying is that if you have the board on a box outside of the orange, and then you connect through USB, you connect also the power through cables, and you have the pin out cable that goes to the orange, and then you can put it on a specific pin. You can say, I want pin 1.
Yes and no, but you have to consider that this board, this board is not powered by USB. It is powered by GPIO.
No, but that's the thing. So you need to power it either directly to one of the orange, to the main orange, or you can have power on its own as well.
Yeah, but in this
So you
case,
can power it.
I need to find out what power lines are used just to boot it up. I haven't checked that yet.
But in this case, our power pins aligned, they are usually on the beginning of the header. And our data lines are not aligned. So this is the issue here.
There are 3 areas where
But what I mean is from a design perspective is that it will be more efficient to deal with the board separately, so that later on, if you have a Raspberry Pi, for example, then you connect the pin to the pin 1 because it's pin 1 for all the boards. You don't have to physically put it on top of it. So it's going to be pin 1, and then you don't need to change the code.
Not quite sure whether I understood you. Your idea is to take the Waveshare hat and not put it on one Orange Pi, but to keep it separate, to power it up via whatever GPIO power there is needed for this board, and then do the rest, like having pin 12. I don't see, where's the pro here? What do we gain by this?
It's just in terms of if later on you have a different board in there, you can always use the same pin. So you can define that you want to use pin 1, and it's pin 1 for all the boards, and it's the same for the code. So you don't need to change anything on the code, because the issue here is that you have the code from GitHub, you download it to the orange, and then you have the pin matching. But if you download it to Raspberry Pi, now you need to change the pin on the code, and you need to figure it out and all of that.
Yeah, but just
so if it's pin 1, then it's pin 1.
It depends on your mapping, on the GPIO mapping in your kernel. So if it depends, I don't know how many chips for the GPIO are used on a Raspberry Pi. I now know on an Orange Pi it's 5 chips, and I know the ranges from what pin to what pin number is which chip. I don't know the very same for Raspberry Pi. But I'm 100% sure
but
that
that's
on
thing,
Raspberry
I also think it is much better to create multiple configurations for each board than to complicate physical wiring. Because me and my teammates from the company, we are making now external PCB which will contain this GPS module, ESP32S3, Bosch humidity, temperature and pressure probes, 5 of them. It will contain a gyroscope, compass and accelerometer. It will also contain output of 12 volts for a PCB heater, which will be under the dome. And we are actually providing like a ports, like a pins where you can insert many USB modules, but we will support this one. So in theory, I would separate this in standalone board and have a pin header which is all for PPS, and to route to each board that requires precise time. and then you just need to flash the ESP32 and it will provide everything through USB and through specialized PPS header. So if you guys have any use of this, maybe we can provide that to you.
Yeah, if you can give us a link or pictures or whatever you have, absolutely.
It's still in design, but it will be done in let's say a few months,
Okay.
2 months.
Okay. Yeah, for me the most important point is that no soldering is needed. So that's why I was
No soldering is needed. Everything is produced by JBL PCB. They have a pick and place machine. They put everything.
I see. So you produce a kind of a motherboard, a breadboard.
Yeah, motherboard for all sensors required for position orientation, RAF orientation, and climate control. Everything except actuators for climate control. You just have reading probes. And the heating of the dome.
Okay.
It will be sold as a kit, so if you guys are interested, because at some point we are going to sell entire enclosures.
Drop it when you are that far that you can show it.
Yeah, definitely. I will put it on our website and share the link.
Cool. Okay. Yeah. What I demonstrated is just one solution. There are certainly others. I've seen Bob using atomic clock chips even. I mean, they are more expensive. They cost around the $500. But with the $110 and something that's just easy to hook up on an Orange Pi, that was my consideration for using this. But there's certainly other solutions, absolutely. But I think with the recipe I set up, it's basically the same way everywhere, and no matter what configuration hardware board you use. If you go with an Ubuntu kernel on a rock chip, for example, then you need to go with user overlays. There's no other way. So maybe you vary from your configuration, but if you go with Ubuntu on a rock chip, then there's no way around overlays, user overlays. Now, okay. Any other question? Otherwise, I stop the recording, which I do now. Bye-bye, guys.